Hello, students. This is Mr. Bornheimer, and in today's lesson, we are going to go over elements and compounds. Okay, and not only elements and compounds, but how elements and compounds form chemical substances. Okay, this is part of Chapter 3 in your textbook, part of Unit 3 under the title Matter, Properties, and Changes. And so if you have any questions, you can either post comments on this video or you can send me an email and I'll do my best to answer your questions. So first of all, we're going to start off with elements and compounds. Okay, elements, and this was trying to be optimized for smart software, so if some of the wordings kind of seem off, like over here, just ignore that. But this is for elements. An element is a pure substance that cannot be separated into simpler substances by physical or chemical means. On Earth, 92 elements occur naturally. Now, you may notice that on the periodic table, okay, periodic table, PT, there are roughly, okay, approximately 118 elements, which means that if 92 occur naturally, there are some, okay, that are man-made. Man-made elements are essentially man kind of synthesizes or puts together protons, and those protons, when arranged a certain way, form new elements. Elements that are man-made oftentimes don't last very long. For instance, elements like I think it's like 112 or 111 only realistically occur for fractions or milliseconds, and then they break down into different elements. So just so you know, elements are pure substances that cannot be separated into simpler substances by physical or chemical means. Okay, so we kind of already have talked about this. Here on the periodic table, we have lots of varieties of different elements. Okay, just to give you a quick rundown on the periodic table here a little bit. Okay, the periodic table. Okay, over here where you see this one. Okay, these numbers at the top represent families or groups. Okay, so when we're talking about families or groups, we're talking about the columns. Okay, so this column over here would be family 1, family 2, family 3, 4, 5, 6, so on and so forth, ending in family 18, which we call the noble gases. Okay, the noble gases over here, they're inert. They don't like to react. Typically speaking, on the periodic table, elements on the far left-hand side are much more reactive than elements on the right-hand side of the periodic table. Some of the names of these substances, like sodium, lithium, calcium, potassium, you should be very familiar with. A lot of these elements are used in vitamins, minerals. Your body needs them. Potassium, your body needs potassium, and calcium for strong bones. Okay, so this is the periodic table, and it's broken down into families or groups. And then the numbers off on the left-hand side here are what we call periods. Okay, so we have periods 1 through 7, hence periodic table of elements. And in chapter 6, we will talk a little bit more about the periodic table of elements and how it's broken down and all of the information that is encoded inside of the periodic table of elements. It's quite amazing. We spent an entire chapter just breaking it all down and looking at it. Okay, moving on. Okay, compounds. There are two or more different elements uh, that are combined chemically. Okay, so you can't physically put two different elements together. Okay, compounds cannot. Oh, I gotta grab my pen here. Compounds are not physical, physically put together. All right, there are 10 million known compounds. That is quite a few. And there are approximately 100,000 new compounds discovered each year. Now, that's incredible. If you break that down by 365 days, that can give you a rough average of how many compounds are formed each day. If you just did that in the calculator, you're probably getting the wow factor. But just to give you an idea, if we're assuming 365 days, not counting leap year, that's about 274 new compounds discovered every day. Okay, and if you were to break that down into 24 hours in a day, just doing a quick calculation here, that's about 11 elements an hour, or 11 compounds an hour. So that's a lot of compounds being created a year. Okay, and compounds, remember, are two or more different elements. They have to be different. There is a substance we will look at like O2, and it's kind of a mix. It's just oxygen, but there are two of them. So what we call this is a diatomic, meaning that there are two elements, or there's an element, but there are two of them. It's not truly an element in the sense that there's a single atom. There's not, but it's not truly a compound in the sense that there are different elements present. So it's what we call a diatomic, and there are some special cases, particularly oxygen gas, which is O2, and then some others as well, like H2, hydrogen gas, so on and so forth. Okay, the law of constant proportions is really the main focus of today's presentation. And the law of constant proportions states that compounds will always combine in the same ratios of the elements. Okay, there's a more descriptive definition on the next slide, but I just want to give you a basic idea of what this means. All right, so let's take CO2. We should all be very familiar with CO2. If you have a paintball gun, it takes CO2. CO2 is used to carbonate beverages like pop, Coke from like McDonald's. Okay, CO2, we're very familiar with this substance. Plants use it in the process of photosynthesis to produce oxygen, which then we breathe. Okay, CO2 is carbon dioxide. Okay, there is one carbon and two oxygens. And this is unique to carbon dioxide, CO2. If there was two carbons, okay, this would be something entirely new or different. Okay, so what the law of constant proportion states is essentially is that chemical compounds, okay, two or more different elements combined chemically, are unique combinations of their elements. Okay, so let's go ahead and look at the next slide here real quick. The law of constant proportion states that when two substances combine to form a compound, they combine in a constant proportion. The ratio of the masses that react remains the same, no matter in what proportions they are mixed. Now, the ticket here is the ratio of the masses. Okay, you're going to want to write that down. No matter in what proportions they are mixed. If there's too much of one substance in the mixture, some of it will just not react. So for instance, let's use our example CO2. Okay, what this means is 1 part carbon and 2 parts oxygen. Okay, if I were to go ahead and take 2 canisters, and this one had 4 carbons, and this canister had 4 oxygens, we could see that the carbon and the oxygens would come together to form CO2. But here's the tricky part. Okay, for every carbon, okay, so we'll just draw a circle here and we'll call this a carbon atom. You have to have 2 oxygens. Okay, so we'll just call this, I'm going to go ahead and scoot this over. Okay, so for every carbon, we have to have 2 oxygens. So here is an oxygen. Okay, and we'll attach it. And here is an oxygen, and we'll attach it. All right, if I have one carbon and two oxygens, then I go down to three carbons and two oxygens. If I use another carbon, it's going to need two oxygens. And then I go down to, and I'm just going to go ahead and erase these. It's going to go down to two carbons and zero oxygens. Okay, and so what we see happening here is this. There's going to be leftover oxygen. I'm sorry, not leftover oxygen. There's going to be leftover carbon. We used only two carbons, but those two carbons had a requirement of four oxygens. They combined in a 1-to-2 ratio. For every one carbon, we had two oxygens. Okay, it's a 1-to-2 ratio. This idea of constant proportions, a 1-to-2 ratio, is what this is all about. Okay, and this last sentence, if there's too much of one substance in the mixture, some of it will just not react. And that's what happened over here with our carbons. We only had enough oxygens for two of the carbons. Therefore, the other two carbons just don't react. They don't do anything. They're just there. Okay, I'll give you another example of this so we can kind of get this down. Okay, and what we're going to do is, okay, we're going to go ahead and switch over to a different colored pen here. Okay, and here we go. Let's look at water. Technically, water is the liquid form, I'm going to put in an L, of H2O. H2O, we can also write it as 2 parts hydrogen and 1 part oxygen. Okay, so for every 2 hydrogens, there is a 1 oxygen is needed. Okay, we can write this in several different types of ratios. We could write this as 2/1, and then this be hydrogens, and this be oxygens. Okay, we could also write this as 2/1 hydrogen to oxygen. Okay, so this is one ratio or way of writing a ratio. This is another way of writing the ratio. And yet we could also write it 1-to-2. Oxygen to hydrogen. If we end up with something like H2O2, that is not water. Okay? Because water has a specific ratio of hydrogen to oxygen. If that ratio is not existent, it is something entirely different. Okay, so this idea of constant proportions for individual compounds is very, very important. Okay, so this idea of constant proportions, please understand how important it is. All right, so this is that. Let's go ahead and take this a step further, and let's look at kind of an example problem. Let us say that we have, let us say that we have 7 oxygen atoms and 24 hydrogen atoms. My question is if this were to react, which of the two elements will be left over. When we approach a problem like this, the very first thing we do, okay, um, is we have to recognize, obviously we're talking about water here, okay, H2O. We want to write the ratio. Okay, we want to write the ratio and look at the multiples. So in this particular case, ratio of hydrogen to oxygen is a ratio of 2 to 1. Okay, and these can be for a variety of we can take variety of multiples of this. So for instance, if I have two waters or two water atoms or H2O molecules, then I have 4 hydrogen and 2 oxygen. And if I have 3, I have 6 hydrogen and 3 oxygen. And if I have 4, I have 8 hydrogens and 4 oxygens. Now, we see that we want to keep going until one of these two hydrogens or oxygens is used up. Okay, so I have 10 hydrogens, 5 oxygens, 12 hydrogens, 6 oxygens, 14 hydrogens, 7 oxygens. And now we see that here we've used up all our oxygens. Okay, we haven't used up all our hydrogens. So if we started with 24 hydrogen atoms and we only used 14 hydrogen atoms, then we have 10 hydrogen atoms remaining. And this is unreacted substances that did not react to form water. It was left over because there was no oxygen for it to combine with. Okay, this is the law of constant proportions. Now, with the law of constant proportions, okay, comes the idea of percent mass. And this might be slightly confusing. Okay, there are some problems in your book that you're supposed to be looking at. And those problems that I gave you today, okay, 9, 24, 12, those problems, all right, have some percent by mass calculations. Okay, so part of this is going to be looking at what percent of a substance is one element, or what percent of a compound is hydrogen or oxygen in the case of like water. Okay, and this is kind of the idea, this kind of stems off the idea of the conservation of mass. For instance, H2O, and we'll just kind of go through a bit of an example here. H2O, all right, has a specific mass. Okay, it has a specific mass. For all our purposes, let us say that we have 18.02 grams of H2O. Okay, now hydrogen is going to be a part of that. So a certain percentage of H2O is going to be hydrogen, and a certain percentage of the compound is going to be oxygen. And if we add those together, that will always equal, anyone want to guess? This is a recording, so it might be kind of weird, but you should try to guess what percentage. You can even say it out loud. That's right, they should add up to what percent? Starts with 1 and ends with 100. Yes, 100%. Thank you. I know you got that all correct. I wouldn't have expected anything less. Yes, the hydrogens and the oxygens, the percent of each will add up to 100%. If I had something like C2H6O2, all right, I would expect that the percent carbon, percent hydrogen, and percent oxygen would equal 100%. Nothing more, nothing less. You cannot end up with more than 100%, and you should never end up with less than 100%. If you end up with more than 100%, you've created mass, and the conservation of mass states that's impossible. And if you end up with less than 100%, that means that you've somehow destroyed matter. And in the conservation of mass states, that's impossible. So the percent of the substances will always add up to 100%. Okay. When I come back, we will go over this percent by mass calculation, and then we will move on to the next law, which is the law of multiple proportions. Thank you guys for watching this. I hope this helps clarify a few things. If you have any questions about the law of constant proportions, please email me and or contact me or write your questions down so that when I come back, I'll answer them. Thanks, guys, and I hope you have a wonderful day.